Hello, and welcome to another episode of Risky Business. Today, we are going to continue where we left off here. I was wondering if n mod m over m is equal to 1 over n mod m. And today, I have the answer. No, it is not. And I will explain why. And I fully figured out what I was confused on yesterday, so I'm gonna go through it with you guys, so we're all on the same page here. So to review, what we were doing is looking at this equation right here, and we found that to compute the speed of the processor, you would do this calculation right here. But then we were wondering, why do they add this to it? And we found out that it's because these are integer operations. So this is like a lossy operation. When you do this division right here, you're losing decimal places. And as a result, the calculation is a little bit off from what the actual value would be. And this is the correction term right here. This is correcting for that. And one thing I want to point out right away is it seems obvious to me, like, couldn't you just rearrange this so you do the multiplication before the division? Because then you wouldn't lose the terms because the value is scaled up already, and then you wouldn't need all of this right here. I'm pretty sure if you just did delta m cycle times uptime frequency divided by delta m time, you'd get the same answer as this right here. I'm gonna ask that on the forums to make sure, but you'll see what I mean in a bit here when we work through it. So we were looking at this last time, and the thing I was confused about is how the correction term actually works. And I figured out that the core of it is really that when you do this mod this divided by this, you're converting a remainder into the decimal portion of the division. That's basically the core idea here. So what we're saying is n mod m, that gives you the remainder. And then if you divide it by m, you get the decimal portion of the number if it were like a floating point division. And in the few examples that we did, it just so happened to be that the remainder, this calculation right here, was equal to this. So that was what was throwing me off. I was thinking there was maybe some relationship there. But it turns out that's not the case. And really the core fundamental idea is this idea of how do you convert a remainder into a decimal. And if you just do long division on paper, you see how it's done. And that'll explain what we're doing here. So I want to show you guys that. So we're going to take a little moment and go back to elementary school here, like 3rd or 4th grade, or whenever you learn long division. I don't remember. So we're going to say, let's do 123 divided by, and let's do 6 because that goes into 12 nicely, right? So obviously this is going to be a 2, and then that's going to be a 0, and then it's going to be 6 times something is 30, that would be 5. It's going to be 20.5, right? So if we just work this out on paper, you do 6 goes into 0, or 6 goes into 1 0 times, right? So you say 1 minus 0 And normally you wouldn't bother doing this part of it because it's just obvious, right? You just skip to the 12. But we're going to work through it all the way because it'll be useful to see what's actually going on here. So we do 1 minus 0, that gives you the 1, and then you bring down the 2, right? Because we're going over to the next place. So now you've got 12 down here. And so 6 times what is equal to 12? Well, that's 2, right? So then you've got 12 down here. You subtract and you get 0. And then you bring down the 3. And we say, how many times does 6 go into 3? Well, 0 times, right? And now we're left with the remainder of 3. So that, if we do 20 mod, or 123 mod 6, you'd get the 3 as the remainder, right? But if you just continue doing the division process, if you just continue doing the long division here, right, this is 123.0, right? And so you bring down the 0, right? And now you've got 30 here, so this is going to be a point up here. And then 6 times what is equal to 30, right? It's going to be 6 times 5 is equal to 30. So you put a 0.5 up here, 30, and finally you get the 0. So you know the division is done. And your answer is 20.5. Well, the question here is, what did we do to convert the remainder, the 3, into this 0.5 right here? And the answer, you can see, is you just divide by 6 again. You just keep dividing by 6 every time, right? So like, 12, we say, how many times does 6 go into 12? Well, that's the same as saying, like, 12 divided by 6, and you get the 2, right? You're continuing to divide into 6. So really, what you're saying is, if you take 3, the remainder of 3, and then you say, well, what is 3 divided by 6? And we said it was 0.5, right? Because you do the 0, and then it's 6 times 5 is 30. Well, you're saying 3 divided by 6 that's the same as saying just like 3 divided by 6. That's what we're doing here. And 3 divided by 6 is equal to 0.5, right? So the process that we do in long division to turn a remainder into a decimal place is the same process that we do when we're just doing long division on the numbers before the decimal place. You just keep doing it, right? So when we say n mod m divided by m, we're just doing that process right here where we got the 0.5. So this converts a remainder into a decimal. And then, well, what about 1 over n mod m? Can we show that that is not equal to this, that it's not always the reciprocal? And this example, I think, will show that as well, because the remainder was 3. So if this were the reciprocal, we would say that this is equal to 3 over 6 should be equal to 1 over 3, and that's obviously false, right? This is 0.5, and this is like, what, 0.33 repeating or something? So this is not true, right? But now we see the intuition behind why this works, right? If you work it out on paper, you see that, you know, you're just repeatedly taking the number, dividing it by 6, you know, and that gives you the answer. So that's the intuition behind why this works right here. And so with that out of the way, I think we fully understand everything that's going on in here, but I want to work through some example, like real world values, rather than working with pretend values that are obviously ridiculous. We're going to take some values that are more realistic here. So we know the f of t in our actual high 5 1. We're using a 32.768 kilohertz crystal oscillator. So it's like the piezoelectric effect or whatever, right? Where you take a crystal and you can produce a pulse at a certain frequency with it. We produce a 32.768 kilohertz pulse. And that's what we use for timing. So if we've got that, and then we say, well, how fast does the high 5 1 run at? And I don't remember off the top of my head. Let's just search like high 5 1, if I can type today. So let's see here. Heard something just fell, but I don't know what it was. I'll look into that later. So if we've got, let's just go to the crowd supply page here. So we can run it at different speeds, of course, but I just want to know like the fastest speed it runs at, and I'm sure they advertise that. So they market it as 320 plus megahertz. So let's go here and say f of c is 320 megahertz. And let's see, what else do we have? We know that the delta t is going to be 10. It could actually be more than 10, but 10 is roughly what it's going to be, because when we do measure CPU frequency, we take a number n in, and we loop until delta until delta m time is greater than or equal to n, right? And see, we're passing in 10 here. So if it happens to do multiple ticks per loop iteration, it could be that it actually ends with delta m time being greater than n, but it's going to be close to n. So we can just say, for the sake of our example, that it's going to be exactly 10, right? Which is probably the case, depending on the speed of the loop. So if we go here, we're going to say that delta t is going to be equal to 10. So we don't know how many cycles it actually is going to run. So we're going to need to find that before we can work through the calculations, right? So the first thing we're going to do is find out what delta c is. So if we look at our equation here, we're saying like delta c times f of t divided by delta t equals f of c, right? Because f of c, the frequency that the cycles are going at, that's the actual speed of the processor, right? So then we want to find delta c in this case. So we're going to say, times both sides by delta t to cancel that. And then we're going to need to divide by f of t to cancel that. And then we should have delta c is equal to f of c times delta t over f of t. So first of all, 320 megahertz, I want to put both of these values in hertz, right? So 3.2 or 32, sorry, 0.768 kilohertz is equal to 32768 hertz, and then 320 megahertz is going to be equal to so it says it's 3.2 times 10 to the 8 hertz. So that would be 3, 2, that's 1, 2, 3, 4, 5, 6, 7, 8. Yeah, I think I did that right. So that's the number in hertz. So we're saying we're doing this number times 10. So I mean, we could just say 3.2 times 10 to the 9th, right? Because we're just taking it times 10. So yeah, that was 10 to the 8th. This will be 10 to the 9th. And then we're saying that is going to be divided by the f of t, which was 32768. And that should give us the number of cycles that run when we time this. So let's see here. 3.2 times 10 to the 9th, and then that divided by 32768. So it gives us 97656.25 cycles. We don't want like a quarter of a cycle. We're talking about like cycles as a unit, right? So should we round it up or round it down? If we round it up, it's running a little bit faster than the advertised speed. If we round it down, it's running a little bit slower. So let's just round it down. We're going to say that we happen to actually be running at, 97656 cycles. So 97656. So because it didn't go into it evenly, I think we need to work through it again and see what our actual speed is going to be, because it's going to be less than this number here. So how do we figure that out? We're going to say, we go back to our equation here of delta c times f of t over delta t. And we know now that delta c is 97656. F of t is just 10, so we just add a 0, right? Or wait, sorry. No, that would be the delta t. We want 97656 times f of t, which is 32768. And then we want to divide that by 10. So let's see what we get there. So 97656. Okay, so this gives us 3.199991808 times 10 to the 8th. So let's write that out. 3, it was 1, 4 nines, and then what? 1808. And then let's see, 1, 2, 3, 4, 5, 6, 7. So the decimal point goes here. Yeah, so that looks correct. So this is the actual processor speed, assuming we do this many cycles. Okay, so now we've got a pretty realistic looking processor speed. And with this here, I want to work through the calculations with the integer math, and then I want to compare it to if you just do the algebra to move the multiplication like I've done here before the division, because I think it's going to give you the same answer either way. So first we do it the hard way. The hard way is you say delta C, so that's 97656, and then divide by delta T, is going to be 10. And now we're like, what we're doing right now is we're imagining that we are the processor. So we're doing integer math right now. So this gives us 9765, right? It should be 0.6, but because this is integer math, the actual calculation loses the 0.6. And this is fundamentally why there's that correction term in there. So we've got 97656, and then we need to take it times m time frequency. So that's f of t. So we say times 32768 hertz. So that would be like this. Okay, and that gives us 319979520. 319979520. 319979520. Is that right? 319979520. 319979520. Yeah, that's correct. Okay, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4. So yeah, that looks correct. So this is what that calculation gives us, right? And the actual value is this right up here. So you see it's off by a fair bit, right? So that's why they put that correction term in there. And so we do 97656. Let's see, and then we do the division first. Or so then we're going to do a mod here. So we're doing 97656 mod 10. So that gives us 6. So there was a remainder of 6. So let's write that out. 97656. And we do mod. Hello, Miblo. So we do mod 10 equals 6. And then we say 6 times the frequency again, I believe. Yeah, and then we're going to divide that by the delta m time. So it becomes 6 times 3, 2, 7, 6, 8. So that equals 196608. Oh, 196608. For some reason I was thinking 7. There we go. And then we divide by 10. And again, we're doing integer division, so it just gives us 1966 We lose the 0.8, which is this 0.8 right here. So then we say this number right here plus this number should equal 319999180. Right, that's the corrected value for hertz, which is only off by 0.8. So you see that's much closer to the actual value. So let's do the addition here and see if we're right. So 319979520. Plus 19660. And we get 319999180, which is what we predicted. Okay, so this is how it actually works in practice, right? Now, this is my suggestion. If we do it my way, which is to just do, we do delta C, so that was the 97656, I believe. Yeah, so we say, here's our cycles, and now we say times the frequency. So that would be 32768. So let's see what that is. So that gives us 3199991808. And then we say that divided by 10, and that gives us the answer of 31999980 hertz. So I feel like they could have just avoided the entire complicated correcting the value thing just by doing algebra and putting this multiplication before this division, right? So I'm going to ask that on the forums, because it seems like we worked it out on paper and it seems to work, right? I don't see why they couldn't just do that. So let's go to the big risky business question thread. Is there any reason we couldn't just do delta m time, or what's it called? It's the cycle one. Delta m cycle times delta, or frequency, what do they call that? M time freak, divided by delta m time, right? Instead of delta m cycle divided by delta m time times m time frequency plus and then the correction term is delta m cycle mod delta m time times m time freak divided by m time, or delta m time. So let's see, did I read that correctly? Yeah, that's how they do it. And that is init.c's measure CPU freq. So I'll say we worked it out on the series that the second part of the equation is correcting for the loss from the integer division. And it seems that you would get the same answer without the correction term if you just rearrange it so that the multiplication happens before the division. Oh, and then I also want to know, also, why is measure CPU frequency attribute no inline? Is there a reason? We don't want the compiler to inline this? Well, Miblo, the rounding error is only going to happen, like, it only happens for the stuff that ends up being a decimal place. So in our examples here, like, the problem area is, let me see if I can find a good place to show you. It's hard to see in my scribbles where we can show you this. But basically what happens is we're doing this division right here before this multiplication. So that's going to cut off, like delta t, we know that delta t is being called with the value 10. So I guess if you want it to take an arbitrary value, if it's not necessarily going to be called with something like 10, it could be that their code is more robust, but in practice, our code does the same thing. So maybe if we change this call site here, we might actually be able to get them to give us different values. So you could be correct that their code is more robust, but this function is only used like right here. So I don't think it really would have mattered. I don't know. We'll see what they say on the forums. They'll probably have a more nuanced answer for us. But anyway, now that we fully understand what's going on here, I think we can move on. So I believe we fully understand the measure CPU frequency, and as a result, we fully understand get CPU frequency. I mean, we don't know exactly why the iCache needs to be warmed up, but that's just like a hardware weirdness thing, just like how you need to do a busy loop in UART init because it needs time for the line to settle, right? Like, that's not something you learn from reading documentation, and it's something that you need to like actually really understand the hardware at a deep level to know like why those kinds of hacks are necessary. And if we study the hardware at some point, we probably will get that understanding and understand all the little nuances of the hardware. But of course, that's something that's specific to every platform. Like a different platform is not necessarily going to have the same nuances that this one does, So, although I'm sure that kind of knowledge does transfer over well to working on multiple platforms, but anyway, let's go back. So, what were we doing that we called get CPU frequency? Let me see here. Were we looking at... Oh yeah, we were looking at UART init, weren't we? So we understand that the IOF selection stuff. And we looked at the URT reg div. Or I don't know if we actually looked at these macros yet, but we understand what it's doing. Right, we saw that this equation matches up with, oh, let me find it again. Where were we? So, we're studying the UART, so let's get back to UART first of all. So that's probably this manual. Yeah, so we have this baud rate divisor. So it's the divisor used by the baud rate generation. So that's defined as this thing, right? So you have the speed of the processor here divided by this div value, which is what you put in a register, plus 1, right? And so we saw here, we're doing get CPU frequency divided by baud rate minus 1, because that's the algebra to get the value div right here in this equation, right? This part right here. So conceptually this makes sense. We just need to take a look at the macros that are being used here, and that should be very straightforward. And then we have this one is doing the TX control register. We're turning on TX enable. So let's take a look at that. TX control register. Oh yeah, so there's transmit and there's receive. So this is only setting it up to do transmission. So presumably if you want it to do receiving off the UART, you need to set RX control, RX enable, right? But let's take a look at TX control first of all. So the read-write TX control register controls the operation of the transmit channel. The TX EN bit controls whether the TX channel is active. So that's this bit right here, it's the low bit. So we're turning that on to say that transmission, the transmission channel is active. When cleared, transmission of TX FIFO contents is suppressed, and the TXD pin is driven high. Okay. So apparently you can actually kind of query for this by checking if the TXD pin is high or not. The end stop field specifies the number of stop bits, 0 for 1 stop bit and 1 for 2 stop bits. So apparently we can actually use 1 or 2 stop bits. I don't know why you would want to use like 2 stop bits versus 1. we'd have to like look into more of like the use case of UART to understand why some things would want 2 stop bits. But for our purposes here, we're just using the default of 1 stop bit. And then the TXCNT field specifies the threshold at which the TX50 watermark interrupt triggers. Right, so that's for having this trigger interrupts. And it says here that the register is reset to 0, so we don't need to like set end stop to 0, right, to manually say that we just want 1 stop bit. It just automatically is that when you do a reset. And then the receive control register looks like it's the exact same thing, except it's for receiving rather than transmitting. And then here we see this table of various baud rates and their divisor values. And then we already know about this. This is just because the UART line needs time to settle before you start using it. So I think we fully understand everything here, other than like the hardware details of the UART line needing time to settle and stuff like that. So we should take a look at the UART 0 reg macro and the UART reg div and TX control. So let me see here. Where is that going to be defined? Let's check the platform thing. This is the IOF stuff. Okay, here's the UART 0 reg macro. And we see it's the 32-bit register dereferenced macro, right? So that's the one that we've seen a lot already, where it just it adds an offset to a pointer and then it dereferences it. So we're adding an offset to the UART 0 base address. I don't remember if we saw the UART 0 base address already, but it's defined right here. And if we look in the documentation, let's check the memory map. UART 0 is defined at base. So 10013000. 10013000. So we see that's taken straight out of the documentation there. And then we need the offset as well. So let's go back to the code here and get a refresher on what our offsets are. We were in init.c, weren't we? Yeah, here it is. So the division register and the TX control register. So that's not defined in platform. Where else might it be defined? Could be an encoding. Nope. Do we have like a, here it is, uart.h. So yeah, here's the div, and here's the tx control, 0x08 and 0x1 is what those are defined as. Now let me see here. Where is that going to be in the documentation? Here they are. So here are the offsets right here. And the names, so control is 0x08, and then div is 0x018. Is that what we saw? This one's 18, and this one's 8. Yeah. So that matches up. So I think we understand everything about UART init now. Let's see. Now, why were we looking at UART inits? Let's go back to demo GPIO, wherever we have that, if we even still have it open. Looks like we do not. Let's open it here. So I think it's in the print instructions that we're looking. So let's find print instructions. There it is. So yeah, like the write, the printf and all that. I think we just jumped into learning about the UART because we know that this uses the UART. But there are a number of different write functions we've seen. We're currently doing printfs in here. The actual original code was doing write calls. So since this one is using write, let's see if we can find the definition of the write call. So it looks like I don't have it open here. Now, where is that going to be? How big is this tree? Pretty big. It's probably under sys, right? Yeah, there's a write.c under sys, and that's in librap. Okay, so this defines a wrap write. I wonder where the wraps are, like we want to see where write is actually defined, and I assume it's just going to be like an alias to this wrap write call. And we see it is doing UART stuff in here. So let's take a look at the make files again. Okay, it does include librap, librap.mk. So there's a librap.mk. Let's take a look at that. That would be the make file for librap. So it compiles all the various things that we wrap. Okay, interesting. Symbols. So malloc, free, open, lseek, read, write, fstat, stat, close, link, unlink, exec-ve, fork, getpid, kill, wait, is a tty, times, sbreak, and exit. So there's the write symbol here. Now, let me see here. There is a for each librap symbol. Dash WL dash dash wrap equals S. So I think the syntax here is saying it's creating a bunch of command line arguments here. It's passing dash dash wrap equals this, and then the dash WL. I think this is to pass arguments to the linker, if I remember correctly. So this is GCC. Yeah, so dash WL comma option passes option as an option to the linker. So I don't know what linker we're using here, but let's just do like man LD. It's probably just using the GNU linker rather than something like ld.gold. So when we say dash dash wrap, so it says use a wrapper function for symbol. Any undefined reference to symbol will be resolved to __ wrap symbol. So this is saying that when we pass dash dash wrap malloc to the linker, it's going to replace every instance where we call malloc with dash dash wrap _ malloc. So then we define the wrapper malloc, and that's what actually gets called. So that's how write is getting defined. So it is actually using that that one we saw in write.c. So let's take a look at write.c. So this is write, right? The linker will replace our write call with this right here. And so it takes the file descriptor, the pointer, and the length, just like the Linux system call. And let's see what it does here. So it gets a pointer called current, which is the pointer you pass in. And then it starts off with is a TTY on the file descriptor. So we're going to need to look at the implementation of is a TTY before we can understand write. So let's take a look at librap's is a TTY. Whoops. Okay, so that's pretty simple. It just says if it's std out file no, or if it's std error file no, then it is a TTY. Otherwise, it is not a TTY. Pretty straightforward there. And I don't know where we're defining std out and std error, but presumably they are defined in unistd.h since we're including those there. So where is our copy of unistd.h is the next question of the day. So let's just do that tree call again. See if we see it there. So it looks like it's not under BSP. So let me see here. We are looking for these standard library. Let's check the make files again. So let's go back to BSP. So there's the toolchain bin. That's giving us GCC AR. We are including a syscdefs.h. Is that from like librap? No. Let's check risc-v GNU toolchain. So there's the risc-v glibc. That sounds promising. Okay, here we go. So here's all our includes. What was the one that we were looking at? Let's see here. We were looking at is a TTY. We want to know unistd.h. So let's see here. Okay, here we go. So can we find no file no in there? It's probably in the posix unistd, I would guess. So do we have a posix directory here? Looks like we do not. Maybe it's under GNU? You'd think it would be under risc-v glibc. Aha, there's a posix directory under there. So let's check out that unistd. There we go. So we're saying standard input is 0, standard output is 1, and standard error is 2, and that's just the normal POSIX definitions, just like we have on Linux. So what we're saying is if you pass it a 1 or a 2 as a file descriptor, is a TTY returns true. All right. With that out of the way, let's go back to looking at the libwrap write.c. So if we pass it the standard input or the standard error, it does this stuff. Otherwise, it returns stub e bad f. So we need to find stub.h next. to understand that part of it. And then once we know that, we get into the juicy stuff. So let's take a look at stub. So is that part of librap? Yes, it is. It's under sys. There's a stub.h. So it takes an integer and returns -1. Okay. So if the write is past a bad file descriptor, it just returns -1, is what that's saying. I don't know the purpose of passing the value in, but we don't really care. So this is the juicy stuff that we want to look at next. But I believe we are out of time today. So tomorrow, or I guess tomorrow's Saturday, isn't it? So whenever I stream next, we will continue looking at the implementation of write here. So thank you everyone who tuned in today, and thank you everyone who watches on the YouTube archive, which is available at risky.tv, and you can follow me at HMN_risky on Twitter to get updates about the series. I will see you next time, and stay risky, everyone.